we have so far discussed about the resistance of ship in deep water. As you know that these vessels which, even though you design it for a deep water country, the ships which operate in deep sea and all that, they have to operate in shallow water also. Whenever it comes to port region, harbor region, it will have to encounter the shallow water effects. So the water depth is restricted and naturally it will be subject to shallow water. We just see what are the shallow water effects, or what would be the effect of the shallow water on the various aspects of operation of the ship. Here the total restricted waterway is, now you can just classify restriction in the transverse direction and also restriction in the depthwise vertical direction. So the vertical direction, you say it is a shallow water if the water depth is less, or if it is the transverse restrictions are there, it is a canal, river and all that, that also come into picture. The shallow water with transverse restrictions aggravate the problem. So that is a general understanding of that problem. So waterway restriction affects the vessel's following character. How it affects the resistance of the ship, increases the resistance of the ship, and when it increases the resistance of the ship, naturally the speed comes down if the vessel is not having sufficient power, or the propulsion system is not delivering the required sorry so required additional thrust for the operation of the vessel. So there is a involuntary reduction in the speed due to the increase in resistance, and that is a resistance part. So the speed comes down. So next is the maneuvering. The ship become more sluggish in shallow water. The responsiveness of the ship is bad, and its response to action of rudder become bad. The controllability of the ship become bad. So that is another aspect. Then the next one is propulsion. The propulsive characteristics also get negatively affected, because the flow condition changes, the flow to the propeller also become bad, and the propulsion performance deteriorates. So here we say the shallow waterways now, we just consider maybe the canal later, we just look to the resistance in shallow waterways. There are different effects. You can see the effect number 1, so potential flow around the ship changes in shallow water. So here we just see that what happens that. So if you consider shallow water region, if you consider, okay, you just consider a ship which is floating at this water line, and you have the bottom very close to that. So that is it. So it is moving forward. So that means the flow is in this direction. The flow comes here and flow is moving in this direction. So the flow, the water ahead of it has to escape through underneath the ship. So what happens is the ship, the waterway is restricted now. So law of conservation of mass, the water here has to move this side. So the flow velocity has to increase because the waterway has been restricted. The flow velocity increases. When the flow velocity increases, what happens to the pressure? The pressure decreases. Bernoulli's equation. The pressure decreases, what happens? The ship will sink more to make up the buoyancy, isn't it? The pressure reduces, it has to sink more to make up the buoyancy. When it sinks more, what happens? The wetter surface increases. When the wetter surface increases, resistance increases, isn't it? There is more contact with water, so resistance increases. So that is one of the aspect. So when it moves forward, due to the constriction at the bottom, the flow velocity increases, pressure drops, ship sinks more, and more wetter surface area and more resistance coming to the ship. Another thing is, that is why it is called the potential flow around the ship, that is the changes in the shallow water. then the flow velocity is, that is what I discussed, the flow velocity higher beneath the ship bottom in shallow water compared to that in deep water. This thing happens even in deep water also, sinkage, but sinkage is very less. When it moves forward, the velocity compared to still condition, the velocity of flow increases, there will be a slight sinkage, but in shallow water this sinkage effect is magnified. So that is the reason. Then another aspect you have to consider is there is a boundary layer formation coming from the, if it is a viscous flow, a boundary layer is formed below the ship, and the bottom which start filling the flow, bottom also will get another boundary layer. So there is a boundary layer attached to the ship, there is a boundary layer now attached to the bottom. So the boundary layer thickness is 0 at this point, and boundary layer thickness increases towards the aft. So when it increases, that means the flow constriction has increased due to the presence of the boundary layer towards the aft. So here the flow, here the opening for flow is more, whereas when it comes to opening for free flow is less. So that means the flow velocity will be higher here compared to the flow velocity here. So that means the pressure drop will be more here and compared to this region. So there is a unevenness even in the pressure drop in the bottom region due to the bottom getting closer to the ship. So this again leads to, that means lower pressure means it will sink more here than sinking here, that means the ship will trim. When the ship trims, that means in shallow water the ship sinks and also it trims. So that combined effect is called squat. You have a squat which is due to sinkage and trim. So you get both. So trinkage and trim leads. So this again leads to the increase in resistance, and also when the ship trims by aft, when it is moving with the you see it is like this, say this like this, the ship, the water level is like this, it is trimming by aft. If it operates in such a condition, then the ship become directionally more stable. It is directly very stable because it is trimming by aft, more area the aft region underwater. So if you have studied this controllability, you know that NV coefficient become less negative or positive due to that trimming condition, and which leads to more directional stability for the ship. More directional stability implies that the ship will be less responsive to the action of the rudder. So if you want to change the direction of the ship in such a condition, it is more difficult than doing it in the even keel condition. So this shallow water effect not only increases resistance, it also leads to trimming. We have seen the squat which leads to trim, and when it trims the ship become directionally more stable, and this leads to less responsiveness to the ship by the during the application of rudder. So that is one effect, and another effect what you consider here is, you can see the waves, that is effect number 2. You can see the wave pattern created by the ship changes as it moves from deep to shallow water. The wave pattern, what do you see? We have seen the wave pattern for deep sea condition as the one put forward by Kelvin wave pattern, which includes that divergent and transverse wave systems. So this wave pattern, wave size changes when it moves, the ship moves from deep to shallow water. So we know that from the wave theory, the shallow water, the wave velocity in finite water depth is the expression given by the wave velocity square is equal to GLW, that is a wavelength divided by 2 pi tan hyperbolic, its h is a water depth, that is a finite water depth. And so this expression given by the wave theory for the wave velocity. So in deep water, that is h is very high, so this quantity is very high, so it goes to 1, the hyperbolic function of tan, and so this velocity gets simplified to, this expression gets simplified to this one. So this term is equal to 1 in deep water condition. When it comes to shallow water, that is water depth is very less, then you have this term taking the tan hyperbolic leading to 2 pi h by L W. So then you just replace this by this term, you get VW square is equal to square root of GH, or V is equal to, I think it is V is equal to, not V square, V is equal to square root of GH, that square is not there, V is equal to square root of GH. So usually for shallow water condition, you know the for deep water condition, the Froude number is length of Froude number, which is represented as V by root GL, L is the length of the ship. But often in shallow water, the Froude number which you use is depth Froude number, so in place of L you put H. So that is what is normally used, because the depth effect on wave formation, Froude number is referring to wave formation, and the depth effect on wave formation is more here, and that is the reason why the depth is used as a parameter here for the representation of Froude number. So when the Froude number, so what the second effect, what you are saying is that the wave pattern size differs when the ship enters from deep to shallow water, resulting in change in the or increase in the wave making resistance also. Froude number FNH, the depth of Froude number, if less than or equal to 1, what is the effect? For Froude number less than 0.4, the wave pattern is enclosed between the straight lines having a angle of this, and this is same as the Kelvin wave, I think, yeah, this is same as the Kelvin wave, what you see. So this angle, this is actually half angle, is 19.5 degrees, okay. And but when it comes to that is what is given, that is just underline, both transverse and diverging waves are present. For Froude number between 0.4 and 1, the depth of Froude number, this angle increases, that is comes out and approaches 90 degrees when it reaches nearly 1. When Froude number reaches 1, the wave pattern, you can see that it goes up to almost 90 degrees, you can see that it go beyond. So you can see the angle here is 19.5 degree, Froude number of 0.4, and here when Froude number is close to 1, the angle has gone closer to 90 degrees. So that is what it means. See, then Froude number is equal to 1, wave travels at the same speed of the vessel, and all the wave making effect is concentrated on a single crest through the point and at right angles to direction. So whole wave, the single wave you see that is a massive wave which moves with that at Froude number, depth Froude number is equal to 1, which is called the critical speed. When the Froude number is greater than 1, then the angle comes down, that is what you have seen here. So the angle here is only 45 degrees, Froude number 1.4 you can see, depth of Froude number 1.4. So this is a threshold point. If the vessel can get over Froude number of is equal to 1, then the power also comes down. So the vessel should have tremendous power to get over that Froude number is equal to 1. And so the for Froude number greater than 1, then the alpha, that's angle begins to decrease again. The wave system now consists only of divergent waves, that is what we have seen. The wave system, we have only divergent waves. You can see that here divergent wave, here you have the transverse waves. Here the transverse waves are present at low Froude number. When Froude number goes up, transverse wave at, in this case below, just near to Froude number 1, you have only one transverse wave. I think that takes the whole energy, and when it crosses 1.1, then you do not have the transverse waves, only the divergent waves are present, you can see here. So that is a characteristic difference of the wave pattern when the speed changes and in shallow water. So also you can see the inner crusts are concave to the line of angle instead of convex in deep water. So it is just coming down, you can see that this is the variation, instead of just going out it is coming down, the trend also changed. So this is the type of different wave pattern, schematic representation of the wave pattern when the speed increases from low speed to high speed and to higher speed. So accordingly you can see what is the depth effect on the resistance of the wave making resistance. You can see the wave making resistance against Froude number. You see that for different h by L, h is a water depth, so h by L small means it is quite shallow water, this is little more deep and finally it goes to very deep. So this is just showing that how the wave making resistance changes or increases with the Froude number and also with water depth. So here you can see this is very high and here water depth is more, it has come down, so it has come down and the least one is when it is in deep water. So from the above figure you can see h by L is equal to 0.75, for h by L is equal to 0.7 by the wave making resistance is maximum at V by root GL is equal to 0.866. You can see that it is against the length of Froude number. So at h by L is equal to 0.75, the maximum point is here and this is read as 0.866, the maximum point, that is V by root GL is equal to 0.86. So that is what is written here, h by L is equal to 0.75, Rw is maximum at V by root GL of 0.866. So here V by root GL is equal to, now L is equal to h by L is equal to 0.75 means h is equal to L is equal to h by 0.75. So now you replace L by this quantity, so you get this relation and which is equal to this into 0.866. So which implies V by root GL of is equal to 0.86 is same as V by root GH is equal to 1. So that what it means. So when you consider the Froude number based on length it is 0.866, but when you consider it based on h it is 1. So this is the critical point, that is the critical condition where the resistance increases. You can see in the previous thing, you can see that the resistance increases at this speed V by root GL, then after that it is coming down. So when it goes to higher speed, if it get over the threshold point or critical point or critical speed, then the powering comes down. So if you can design a vessel which can get over that, and then the resistance comes down and you need only less power to operate the ship at a higher speed. So here you can see the Froude number less than 1 is termed as subcritical and Froude number equals 1 termed as critical speed and greater than 1 is called the supercritical speed. So that is how the classification of the speed of the vessel in shallow water. So this is all depending on the depth Froude number. So this is how the speed of the ship is classified based on the depth Froude number. The resistance and wave pattern, Rw increases with Froude number h, we have and reaches the maximum we have seen at Fn is equal to 1 and then it decreases further with the Froude number, isn't it? We have seen that from the previous diagram, it goes up, reaches a peak and comes down. When it reaches a peak Fnh is equal to 1, then Fn greater than 1 the resistance comes down. So displacement vessels travel in subcritical speed. You can see normally most of the displacement vessels such as the cargo ships and all that, they are displacement types and they operate at a Froude number or Fnh less than 1, except high speed vessel ferries, HSV high speed vessel, high speed passenger ferries and all that. It also destroyers, there is a naval vessels which go at a very fast speed. So these vessels will be operating at supercritical range. As h decreases, speed of the wave of a given length also decreases. When the water depth decreases, wave speed also decreases. We have seen that Vw is equal to square root of Gh. So when the depth h decreases, Vw decreases, isn't it? That is a relation. In shallow water we have seen that. So this is a statement based on that relation. Thus, to maintain the same wave pattern, a ship moving in shallow water will travel at a lower speed than in deep water. So that means a ship in shallow water will move at lower speed in lower speed than in deep water, because when the depth decreases, speed also decreases. So we consider they move at the same speed. Ship and wave relations. In order to generate a transverse wave with wavelength Lw, the ship is required to have the speed of that of the wave. The ship wave speed is Vw, the ship is also going to have a same speed. So that means the wave is moving at the same pace. In deep water, the ship speed, we have seen that it is coming from the wave theory. It is V infinity square is equal to G into wavelength divided by 2 pi. This is a relation for wave celerity or wave speed. In finite water depth, this relation we know that we have already seen this expression before. Finite water depth, the same wavelength would be generated at some lower or intermediate. We have seen that the speed comes down in shallow water, and so the velocity also comes down when the depth decreases. So this is a relation for finite. So there is a intermediate, I stands for the intermediate speed. So this velocity is going to be less than this. So in order to generate a transverse wave with wavelength Lw, the ship is required to have the same speed of that. So the wavelength required the transverse wave with the wavelength Lw, the ship is required to have a speed of the same as the Vi, that is Vi is given by this relation over here. So the ship also will move with the same speed, that is here Vi is equal to Vwh. The ship speed, intermediate ship speed is equal to, that is the wave velocity at the finite depth. Ratio of these two speeds, Vi by V infinity, we have seen the expressions of Vi and V infinity squared by this, Vi squared by this. You take the ratio of that, you get this relation Vi by V infinity is equal to this one. So this is a relation which you get from the previous one. So the Vi is less than V infinity, so that difference in speed delta C is given by V infinity minus Vi. So here the procedure is just trying to find out the resistance in the shallow water region if you know the deep water resistance. So that is what is trying to do here. We are trying to find out how it is done. So the reduction in speed in shallow water is this much due to the wave making. Schlisting assumed that this is called Schlisting's method. So he has assumed that the wave making resistance shallow water at speed Vi would be the same as the speed V infinity. So the shallow water, there is a wave making resistance at a reduced speed in shallow water is same as the wave making resistance at a higher speed V infinity in deep water. That is the assumption. So what you have here is, you consider this is Schlisting method. You can see the shallow water resistance by Schlisting method. It's a method proposed by Schlisting. So you have this one, the purple line here, that shows the total resistance of the vessel in deep water condition. This is, we have discussed about resistance, model test, everything in deep water. So we have already this information with us, that is the deep water resistance of the vessel can be estimated, and we have seen the procedures for estimation mainly through experimental procedures, that is model prediction and model resistance and predicting to the prototype. So that means this curve is available to us, and it is a straightforward or prescribed method for that. So now you have this line over here, that is R of, that is a frictional resistance again deep water, which is coming from the viscous effect we have discussed. We have seen that from that frictional resistance how it is estimated. So now what you have, and then finally you will get, once you follow through the resisting method, you will come to know what is the resistance in shallow water. Okay, and here this is a procedure. What you have is, you have the frictional resistance, the V infinity, that is a deep water condition, you have it here, deep water condition. Up to this you have the frictional resistance at infinity refers to deep water condition, that is a frictional resistance in deep water condition. Then you assume this is a one from here to the total resistance, that is the wave making resistance in deep water, and here resisting assume that the wave making resistance remains same at a reduced velocity of Vi. So what is that? You estimate what is delta C. If you can estimate delta C, you can find out this point, what is the delta C, and then you find out what is the frictional resistance curve, what is the frictional resistance here, and to which you assume the same wave making resistance at this speed and also at this speed. So you just plot the same wave making resistance over this, so you get this point, point B, and then you have the effect due to the frictional effect, or not the potential effect what I discussed, sorry, the potential effect. So you have the velocity reduction due to the additional resistance coming from there. So from which you get point C. We see the procedure adopted here. Determine the shallow water resistance by listing it. What is the procedure? The deep water Rf infinity, Rt infinity are the frictional and total resistance of particular, this we know, we have already estimated that. So the curve, the graph is available. Schlisting assumed that the wave making resistance of the ship depends only on the wavelength of the transverse waves of the system generated by the ship. So its wave making resistance is now primarily due to the transverse waves, that is the assumption made by Schlisting. The transverse waves assumed to be the sole contribution of RW appear to be locked with the ship, and so that means they move in the same pattern. We have seen that Kelvin's wave, the ship will have a steady wave which is moving with the ship. So here he assumes that VW, the wave speed, is same as the ship speed. That means it looks like the whole wave is moving at the same phase with the ship, but its amplitude is independent of both VW and LW, but the amplitude of wave in deep water and in shallow water are going to be different. And you know that the amplitude of the wave is the one which actually determines the wave resistance. So when the amplitude increases, wave resistance increases. The speed at which the certain wavelength is generated and therefore at which the certain wave making resistance is set up is depend on h. So you can see that the speed and wave making resistance is depending on the water depth. The total resistance at speed Vi would then be found at by point B adding Rw. So that is what we have done here at B, that is the total resistance at Vi is equal to the frictional resistance taken at that point plus the wave making taken as same. So you just put the same value measured here Rw infinity over the frictional resistance for that lowered speed and you get point B. That means these two lines are parallel, that is AB and FE are parallel, that is what it means. So AB is parallel to FE, so because you are putting the same value. Further speed loss delta Vp because the increase in flow around the hull, that is what I discussed in the board. So due to the constriction there will be a flow velocity and there will be a increase in resistance due to the pressure changes and sinkage and all that. So I have already discussed the squat effect. So it is coming from the squat, this further reduction in the pressure because of wetter surface increase and so. How do you get that? The final speed will be Vh is equal to Vi minus delta Vp, isn't it? That is this is equal to Vi already we have seen there is a reduction in speed and then due to wave making, and then you have to find out what is the effect due to this potential flow, that is the restrictions. The principal factor controlling delta Vp is the ratio. So what you have to look is this depends on the constriction, that is Ax is the midship area of the ship and H is the water depth. If the water depth, this factor actually what is the size of the ship and what is the water depth, which matters in determining the constriction and then the flow velocity and increase in resistance. So Ax is the maximum section area of the hull and H is the water depth. So a curve has been presented by Schlichting based on his studies, experimental studies. You can see that he has given for plotted Vi by V infinity and also Vh by Vi against V infinity by square root of Gh against Ax by H and Ax by Rh. This we see Rh later. So what you have is, you see that there are three curves here. One, this curve, it is the curve of Vh by Vi against square root of Ax by H. You have another curve, you can see here this curve which is Vi by V infinity to the base of Vh by Vi, and then the third curve that is coming from the Landweber, which is Vh by Vi against Ax by Rh. This is a hydraulic radius, we see it later. So from these curves we will be able to identify, if you know this quantity V infinity by Gh, then you will be able to find out this V once you know this quantity square root of Ax by H, and I think there is a mistake here, this square root is only from the top, it is not to the bottom, it is square root of Ax by H. And you can use this graph and find out the speeds. We will see how it is approached, we will see in the subsequent steps. So the figure which shows Vh by Vi for value of Ax by H, we have seen this one, this graph is referring to this Vh by Vi against Ax by, so this is the graph. So what you do is, you use that graph, then this V delta Vp is equal to, so what you do is, you can read for, you know what is the midship area of the or maximum area of the ship, and you know what is H, again this mistake is there, it should be the square root on the top. So what you do is, you for this value you can estimate by knowing the ship and also the water depth, then you use the graph, you find out what is this value, then you maybe 0.6, you just come here and then you read what is Vi by Vh by Vi, so you can find out this quantity from here. So from which you get this quantity, and you know that delta Vp is equal to Vi minus Vh, and you divide it by Vi, you get this relation, okay, from this. And now you have read the value of Vh by Vi, so you have already done that, from which you will be able to find out this quantity. This is coming from the graph. Now again from the above graph, you know what is the free stream velocity of the ship, speed of the ship divided by this Froude number, depth Froude number. So once you know that, you go there and you see there is the curve which is representing this one. I think there is again a mistake, this is against this one. So you get Vi by V infinity, this is actually the Froude number. So you get this curve, and from this you read what is the Vi by V infinity. So that is why you get Vi by V infinity by knowing this quantity from that curve. So delta C is equal to V infinity by Vi, which you have already seen, and hence by same dividing by V infinity you get this relation. So Vi by V infinity is obtained, you substitute it here, you get what is delta C by delta infinity. So you got this quantity by Vi and you got this quantity by, so we are looking for these two quantities, let us see what happens. So you look to the chart, what you have seen now, the speed reduction used due to more wave making in shallow water is delta C. So you just see that this chart, so here just one second, it's in this. So here what you see is that this delta C total velocity reduction is delta V, the one part of it is coming from the wave delta C and another part of it is coming from the potential thing delta V. That is why we said initially there are two effects, effect 1 is due to the potential effect of squat, effect 2 is due to the wave making difference. So these two accounts for the total reduction in speed. Now our intention is to find out what is delta Vp and what is delta C. So that is what we have done now. You can see what is delta C and what is delta Vp. So these things we have to find out. So the speed reduction due to potential flow effect in shallow water is delta Vp is set in a horizontal to B from B to BC. So that is what is done here in the graph. You can see that we have already seen B, how it is obtained, and from B you put C, that is delta Vp, you get point C. Okay. So what you did is, I repeat that this is a total resistance curve in deep water, this is the frictional resistance curve in deep water, and for the deep water velocity you find out what is the frictional resistance from this curve, and the above this you get the wave making for the deep water condition. Okay. Now we consider the Vi, that is intermediate speed due to the higher wave formation, high wave resistance, the speed reduces. Vi, at Vi what is the frictional resistance, but we assume the wave making remains same at that lower speed. So then you put the same wave making here, you get point B, and from point B, from the curve we have got what is delta Vp, and you put delta Vp in this direction horizontally, you get point C. Okay. So for one point A in the resistance deep water curve, you are getting a point, corresponding point for the shallow water. So what you do is you repeat this for various number, various speed, then you get points all over and you connect it, you get this curve, the red curve which represents the shallow water. So that is how the shallow water resistance is estimated from a known deep water resistance curve. So this is a method proposed by Schlisting. He made lot of assumptions here, assuming the same water resistance remain at this speed and all that. So many assumptions he made, but within that he has found, using that he has found C is the corresponding point. But if you look the point A, and if you consider the same resistance, the speed should have been at H, that is this should have been the speed. You can see that the H should have been, this point should have been at H. We will see that what is discussing about that. So here that is what is that, C will be a point on the curve total resistance in the shallow water. Okay. In shallow water of the corresponding speed is Vh. So you have got point C, and if you read it below you get what is Vh. Repeat this for number of points, you get the reverse curve for shallow water. That is what I said, you repeat, we have seen example for one point, you repeat for all the points in the deep water resistance total curve, then you get corresponding points in the shallow water curve, and you connect the points, you get the resistance curve in shallow water. This is a Schlisting method for resistance estimation in shallow water. So note that at point C the total resistance in shallow water at speed Vh is less than that at point A. That is what I said, I think before. Here if you consider resistance at this point and at this point, the resistance at this point is less, or for the same resistance, the speed which can be acquired is more than that at this point. So why this happens? So that is the speed reduction due to, yes. So note that point C, the total resistance in shallow water at speed Vh is less than that at the point A. So the speed in shallow water for this same RT infinity is approximately H, we have seen that point H, for the same resistance it should have been at H, but we got it at C, which is reduced speed based on Schlisting method. So the total speed loss delta V is equal to, we have seen, delta C plus delta Vp. This is due to wave and this is due to the potential effect, we have seen that. So percentage reduction delta V divided by V infinity compared to the deep water V condition, the percentage can be represented by total reduction V infinity minus Vh divided by E infinity. So you can see that the percentage, this diagram shows that if you have the restriction square root of Ax by H gets V infinity by Gh. So these diagrams, what do you see, shows a percentage. So Ax by H small value means H is high, that is water depth is high. So when the water depth is high, you can see that the values are, these percentage values are less. When the water depth is less, then this value goes up and we find that the percentage increase in, or percentage of the velocity which you have seen here, this percentage is going to be higher. So here the Schlisting method is a good engineering solution. We have seen lot of approximations here, assumptions here, splitting it into velocity potential effect, splitting it into wave effect, and assuming that the wave making resistance remains same at a reduced speed, that is an assumption. So there are some assumptions which are difficult to be supported by scientifically, but we made some assumptions, and what it does is trying to find a solution for that. Otherwise, to find the resistance of a ship in shallow water is rather difficult, often is impossible. So here he makes some assumptions, try to simplify the procedure, a practical solution to find out the shallow water resistance. So the assumption of equal wave resistance, that is what I said, equal wave resistance in deep and shallow water are questionable. So you do not know, it is an assumption, but there is no proof for that. The waves will be steeper and therefore higher RW in shallow water. In shallow water the waves get steeper because of accumulation of energy, and the wave gets steeper and the resistance will be higher, RW will be high. The speed, that is actual thing, the speed reduced for the point C will be somewhat too high. That means you have assumed the speed up to point C is very high. So this will partly offset the fact that for the same total resistance the speed should be somewhat higher, that is for the same wave resistance we should have had a little higher speed than that of H. So it assumes that if you look to the curve, what is the listing chart, it assumes that this reduction what assumed may be too high, so it should have been somewhere little this side, so that the total point this C may come closer to H. So that assumption it may not be correct, that is what it means. Considering the above uncertainties, point C may be close to the estimated shallow water. So you have a prediction, one is over prediction, there is an under prediction. So these two combinations will result in approximately the point C as a better one. So these are the the method what is used in Schlisting, and this gives a practical solution, engineering solution for the problem of shallow water resistance, which is evolved from deep water resistance. So in restricted waterways we have seen what are the limitations, what is the effect. One is due to the wave making resistance increases, and other one due to the sinkage there will be more wetter surface and subsequently more resistance coming due to that. So these two accounts we have seen the speed reduction in delta C and also delta Vp, there is a potential effect. The total effect accounts for the total reduction in speed. So that is what we say. There are the assumptions made by Schlisting are not fully justified, but since it is giving a good practical solution, the method is still adopted.